All right, here's the math behind what we're doing in this lab. I'm going to have something on a string that's spinning around in a circle. Now, if it's spinning around in a circle, this is, again, over from a side view. I'm going to have a tube right here. And then I'm going to have a string with a mass attached to the end. And this string is going to be flying out here, and I'm going to have another mass here. So I'm going to be spinning this mass around. This is a side view. Spinning this mass around, and this one's going to be hanging here. I'm assuming there's no friction acting up here, and that's a key assumption. There are two places where this lab where you get the strange data. One is that assumption right there, and the other one is this mass is not going to be hanging directly out like that. But if I dealt with it at an angle, like reality, then that requires trig, and the math becomes far more complicated, and you really don't gain that much. I've done this lab with assuming that it's stretched out like that, and I've done the lab where it's like this. The results are not significantly better. So, and I've done it with the reducing friction here, and the results are not significantly better. Now, if this is my ideal situation right here, so this thing is spinning around like this, I want to do a force diagram. I need to look at the forces. So if I look at the force acting on this object right here, I have a tension acting inwards. If I look at the force acting on this right here, I have its weight acting down. I'm going to call this mass 1 and mass 2. So this is M1G, that's the weight acting down, and then acting up, I have a tension. Now, if this is not moving right here, ideally this thing is not moving, this is just sitting right here, and that thing is spinning, this mass 2 is spinning around, then this is an equilibrium. If it's an equilibrium, that means the sum of the forces acting on it must add up to 0. In other words, well, let's assume that up is positive. That means that tension minus M1G is equal to 0, or the tension is equal to M1G. What I'm claiming here is that the tension in the string, which again we're assuming is constant, the tension in the string is equal to the weight of what's hanging out down here. Well, looking over here, you might be asking, well, what about the weight of mass 2? Doesn't it have a weight? Well, it does, but that's where I talked about earlier, the fact that we are assuming that it's directly out like this. The only way that this thing could be directly out like this instead of slanted down is if the weight is not significant. If the weight is not acting on it, or is we ignore the weight, then the thing actually would be out like this. And so that is the assumption we're working on right here. It's a bit of reality. I'm doing a hand wave to get rid of it, just because to simplify the math. Now, taking these simplifications, this is known as zeroth order approximation or first order approximation. It's done in physics a great deal, and you generally do your zeroth order approximation to get a quick and dirty idea of what the numbers look like, and then as the math allows, because there's sometimes they only go to first or second order approximations because the math, we don't have the math to solve some problems. This one we do, but we don't have the math to solve some problems, and so doing these approximations, at that point you start needing to use supercomputers, and then how far you go depends upon how much time and money you have. But for right now, we're going to keep it simple. We're ignoring the weight on this one right here, and when you do this experiment, the mass of this one should be significantly less than this. And we have a tension acting in. Well, F equals MA. Again, F equals MA. The force is the tension. It is inwards. I'm going to assume that's my positive direction right there. My mass is mass. That's mass 2. And my acceleration, this is centripetal acceleration. The thing is traveling in a circle, and therefore I use my centripetal acceleration formula. That should be equal to the speed squared divided by the radius. That's this radius right here. And so at this point, from this one I know the tension is equal to its weight. From this one I know the tension is equal to mass 2 times v squared over r. And so I then just equate the two. If I'm assuming the tension is the same, then I end up with this grand formula here that the weight acting on the bottom mass, m1g, is equal to m2g v squared over r. Now in this particular lab, you're going to be doing several of these things. You're going to be finding the force, you're going to be finding the speed, and you're actually going to do a plot of force, of this force, that's the centripetal force, times speed squared. And it's speed squared because you got a squared right there in the formula right there. And so therefore, the slope should be equal to m squared over r. We'll do that in analysis when we're going to run through a quick trial, and then I'll make up some numbers just to give you an idea of the analysis.